Welcome back, class. Believe it or not, today is the last lesson in our unit on quadratic equations.
Aw, I can't believe it's almost over.
Mr. C, will you be teaching our next math unit?
I'm not sure, Ruby.
Mr. Caldwell, this is the only non-terrible math class that the Drac has ever taken. I do not wish to leave.
If your grades do not improve, I think that can be arranged.
Class, that's very kind of you, but you're all ready to move on to the next level of math. I'm so proud of how much you've all learned in this class. Now let's finish strong. To finish our unit, we're coming back to a topic we haven't seen for a while: graphing. We've spent the last few lessons learning different methods for solving quadratic equations, so now we're ready to use them to help us graph a parabola by hand. We know that when we graph a parabola, we're really just calculating a few points on that parabola and drawing a curve between them. It's like a game of connect the dots. The only catch is that we can't use any old points on our parabola. We need to start with the most important points. At least 3 of them, or else we might not have enough information to draw our parabola correctly. So no matter what quadratic equation we have to graph, what are the important points we want to start with?
The vertex is important. It shows us where the parabola changes direction and turns back.
Excellent, Codette. If we can figure out where our vertex is, we'll know where to start drawing our graph. And since the vertex is right in the middle of the parabola's 2 arms, the vertex helps us draw those too, since we know the arms of a parabola are always mirror images of each other, reflected across the line that goes through the vertex. Alright, who can tell me another important point for graphing?
The X-intercepts are important. They tell us where a parabola touches the x-axis.
Good, V9. Some parabolas have 2 x-intercepts, which is like getting 2 points on our graph for the price of 1. But other parabolas have just 1 x-intercept, and some have no x-intercepts at all. That means that figuring out our x-intercepts can sometimes be a big help when we're graphing, but sometimes it can be no help at all. Alright, who can think of one last type of point that helps us graph a parabola?
There's also like the Y-intercept. You taught us there will always be one of those because the arms of a parabola keep going forever. So every parabola crosses the y-axis eventually.
That's right, Bones. That finishes our list. When we graph a parabola, our most important points are the vertex, the x-intercepts, and the y-intercept. Good. Now one last thing before we start graphing. It can be very helpful for us to know whether our parabola is going to open upward or downward. Otherwise, when we figure out a parabola's vertex, we still don't know if that's the highest or lowest point on our parabola, the maximum or the minimum. So I'm going to add this to our list. We want to know whether our parabola will open upward like a smile or downward like a frown. Now that we know the points we're looking for, the focus of today's lesson is how we can use our equation to figure out where those points are located. So let's turn now and look at our equation. We know that a quadratic equation can show up wearing different disguises. We usually want to remove any disguise before we start. What I mean is, we usually write a quadratic equation in standard form, which is like a recipe where we write the x squareds first, as our first ingredient, and then the plain old x's second, and finally the regular number at the end. But sometimes, a math problem might ask us to graph an equation that's not in standard form. The equation might be given to us in vertex form, or in factored/intercept form. Those make the equation look very different from standard form. These are all the same quadratic equation. So how do we turn vertex form or factored/intercept form into standard form so that we can graph them easily? To remove the disguises, we use our FOIL technique. Foiling an equation that's not in standard form shows us what it looks like in standard form.
Hold on, Mr. C. I want to make sure I understand. You're saying that if a math problem asks us to graph one of these other forms, we should just FOIL it to get standard form, and then graph that?
Exactly, Ruby. Even though the other forms do give us some clues about specific points on our parabola, we'll be able to find everything we need when our equation is in standard form. Remember, standard form shows us our three ingredients in a row. First the x squareds, and then the x's, and then the regular number at the end. So if that's not what you see when you start, just use FOIL to remove the disguise. Alright, let's erase the other forms on the board and focus on graphing our standard form equation. First, let's figure out whether the parabola for this equation is going to open upward like a smile or downward like a frown. Can anyone tell me, just by looking at this equation, which one it's going to be? Tom, you've been quiet today. Can you help us with this?
Mr. Caldwell, I have an idea. You taught us that to turn a parabola upside down, like from a smile to a frown, we multiply the equation by -1. So I say to myself, Drac, if an equation already starts with a negative amount of x squareds, then I think the parabola will already have a frowny face. It will open downward. But if the equation starts with a positive amount of x squareds, then the parabola will be smiling. It will open upward. It is like you taught us. Positives make us smile. Negatives make us frown. In this equation, we have 1 x squared at the beginning. That is a positive amount, 1. So our parabola will open upward, like a smile.
Excellent, Tom. When a quadratic equation is in standard form, we say that the amount of x squareds it has is called a, and the amount of plain old x's is called b, and the regular number at the end is called c. In our equation, a is +1 because we have a single x squared, just one x squared. B is 6 because that's how many plain old x's we have, plus 6 x's. And c is 8 because that's the regular number at the end of our equation. So what you just told us is that a parabola will open upward if its a value is greater than 0. It will open downward if a is less than 0. In this equation, since a is a positive number, our parabola will open upward like a smile.
Yes, that's what I said.
Good. Then our next step is to figure out our vertex. That's the first important point we always try to graph. Does anyone remember how our a, b, and c values can help us with this too?
You taught us that we can figure out the x-coordinate of our vertex using the expression -b divided by 2a. If we plug in our a and b values, that will tell us the x-coordinate. And then we plug that number back into our equation to get the y-coordinate.
Well done, Codette. We're going to use this equation a lot when we graph parabolas, so it's worth memorizing. Let's see how it works. In our equation, b is 6 and a is 1. So -b over 2a is -6 divided by 2 times 1. That's -3. That's the x-coordinate of our vertex, -3. That means that our vertex will be a point somewhere along this line. We just need its y-coordinate. But let's pause here for a second, because this line is useful by itself. We said earlier that the two arms of our parabola are going to head off in opposite directions from our vertex. Since those two arms are going to be mirror images of each other, any point on one side of this line will have a twin point on the other side, at exactly the same distance. So this line is known as the Axis of Symmetry. It's just the line that goes up and down through our vertex, -b over 2a. Let's keep this in mind, because the axis of symmetry is going to come in handy later. Okay, so how do we figure out the y-coordinate of our vertex, so that we know exactly where on the axis of symmetry it's located? Can you help us, Wendigo?
We have already said that the x-coordinate is -3. Therefore, we can plug in -3 for x in our equation, and this will tell us what number y is when x is -3. When I do that, I get y equals -3 squared plus 6 times -3 plus 8. That simplifies to y equals 9 minus 18 plus 8, so y equals -1.
Well done, Wendigo. So now we have the x-coordinate and y-coordinate of our vertex, which means we're ready to graph it. Our vertex is at the point -3, -1. And since we already figured out that our parabola is going to open upward from this vertex, we know that all of our other important points should be above this point. Think about what that's telling us. If both arms of this parabola open upward, then how many x-intercepts are we going to have? How many times is this parabola going to cross the x-axis?
Mr. Caldwell, the Drac is on a roll. When the arms of this parabola go upward, one arm will cross the x-axis to the left of the vertex, and the other arm will cross the x-axis to the right of the vertex. We will have 2 x-intercepts.
Excellent, Tom. All we have to do is figure out where those x-intercepts will be. To do that, we're going to use one of the methods we learned for solving quadratic equations, for instance the quadratic formula, or one of our factoring techniques like the product-sum method. It's your choice which method to use. Choose whichever one is most comfortable for you and fastest at solving the problem. I'll show both of the methods I just mentioned, but you would only need to choose one method. First, let's use the product-sum method. We start by factoring this equation into 2 sets of parentheses. Each set of parentheses is going to have an x at the beginning and then some number at the end. Our job is to find those numbers, because those numbers will help us figure out our x-intercepts. The clue that helps us is that the 2 numbers we're looking for need to have a product of our c value, which is 8, and a sum of our b value, which is 6. So what 2 numbers multiply together to be 8 and add up to 6?
Like 2 and 4. 2 plus 4 is 6, and 2 times 4 is 8.
Good, Bones. So we put those numbers, 2 and 4, into our parentheses, and that's it. Our quadratic equation is now in factored or intercept form. Y equals x plus 2 times x plus 4. We're very close to knowing our x-intercepts. How do we find them using this equation?
Like any number we can plug into the parentheses to get 0 is an answer. So -2 will be a solution because -2 will turn the first parentheses into 0. And -4 will be a solution because it will make the second parentheses 0. I think those are our x-intercepts, -2 and -4.
You're right, Bones. Let's graph them. Notice that they're exactly where we expected them to be, a little bit higher than our vertex, since we know that our parabola opens upward from the vertex, and also mirror images of each other across the axis of symmetry. Now let's pause here. I promised that I would also show you how to get the same 2 answers by using the quadratic formula instead of the product-sum method, because remember, you can choose whichever method you want. So let me go back and do that. I can easily remember the quadratic formula thanks to the handy song you all sang for me. It's x equals -b plus or minus the square root of b squared minus 4ac all divided by 2a. Now we plug in our values for a, b, and c. We get x equals -6 plus or minus the square root of 6 squared minus 4 times 1 times 8 all divided by 2 times 1. That's x equals -6 plus or minus the square root of 36 minus 32, all divided by 2, which simplifies to -6 plus or minus the square root of 4 over 2. We get 2 answers, x equals -6 plus 2 over 2, which is -2, and x equals -6 minus 2 over 2, which is -4. Notice that those are the same 2 answers we got when we used the product-sum method the first time around. Either method works. Alright class, we've graphed our vertex and our 2 x-intercepts. That makes 3 points, and we said that 3 points can be enough to graph a whole parabola. But in this case, it would be nice to have one more point higher up on the arms of the parabola, just so we can draw more of its shape. So let's go ahead and figure out our final important point, our y-intercept. The good news is that this is the easiest point to find. Does anyone remember how to find the y-intercept of a quadratic equation?
Affirmative. The y-intercept is the point where a parabola crosses the y-axis, so it is where the x-coordinate is 0. Therefore, all we have to do is plug in 0 for x in our equation.
Nicely done, V9. That's right. Let's do it. Our equation is y equals x squared plus 6x plus 8. Ruby, can you plug in 0 for all of our x's?
Sure, Mr. C. We get y equals 0 squared plus 6 times 0 plus 8, which just simplifies to y equals 8. It's really just the number at the end of our equation, the c value. Our y-intercept is the point x equals 0, y equals 8.
Good. And now we can see a lot more of our parabola on this side, which also helps us with the other side too, because remember, parabolas are symmetrical. If we know what one arm looks like, then the other arm will be exactly the same, reflected across the axis of symmetry. We just finished our graph of y equals x squared plus 6x plus 8. Well done, class! You've just learned the basics of graphing a quadratic equation. We started by figuring out whether the parabola would open upward or downward. Then we calculated our most important points, and we connected the dots. Let's try a harder example now to finish our lesson. Let's graph the equation y equals negative x squared minus 4x minus 7. Our first step is to figure out whether our parabola will open upward or downward. Tom, can you help us with that again?
This would be my pleasure. If our equation has a positive amount of x squareds, then it will open upward, like a smiling face. Positives make me smile. But if the equation has a negative amount of x squareds, then it will open downward, like a frown. Negatives make me frown. This equation begins with negative x squared. One single negative x squared. So, this parabola will open downward, like a frown.
Excellent, Tom. The number of x squareds in our equation is our a value, and when our a value is positive, the parabola opens upward. When a is negative, the parabola opens downward. Since Tom just helped us to figure out that our a value is -1, can someone else tell me our b and c values?
B is -4 and C is -7.
That's right, V9. These three values are about to come in handy because our next step is to figure out our vertex. We start by finding the x-coordinate of the vertex using the expression -b divided by 2a. What does that equal here?
-b over 2a means -4 divided by 2 times -1. On the top, the negatives cancel out, so our answer is 4 divided by -2, which is -2.
Good. So the x-coordinate of our vertex is -2. That means our vertex will be somewhere along this line. We just need to figure out its y-coordinate. But remember, this line is helpful by itself because it's our axis of symmetry. The two arms of our parabola will be mirror images of each other across the axis of symmetry. Now let's plug our x-coordinate into our equation to figure out the y-coordinate of our vertex.
I can do it, teacher. When we plug in -2 for x, we get y equals -2 squared minus 4 times -2 minus 7. When we square -2, we get +4. Then our equation says to make this amount negative. Therefore, we have -4 plus 8 minus 7, which is -3.
Right, Wendigo. So our vertex has a y-coordinate of -3 to go with its x-coordinate of -2 that we already figured out. Now we can plot the vertex on our graph at the point -2, -3. Done. Our next step is to find our next important points, the x-intercepts. But does anyone notice a problem we're about to run into?
Ooh, I think I know. Tom told us that our parabola opens downward, like a frown. And we just figured out that our vertex is below the x-axis. So both arms of our parabola will go downward from there. That means the parabola will never get high enough to touch the x-axis. We aren't going to have any x-intercepts to graph.
Excellent, Codette. This is why our equation is harder to graph than our last example was. We said that a parabola might have 2 x-intercepts, like in our last problem, or only 1 x-intercept, or even no x-intercepts like this one. We still need 3 points to graph our parabola, but none of them will be x-intercepts, since there aren't any x-intercepts for this parabola. This shows us why we wanted to figure out, right at the beginning, if our parabola was going to open upward or downward. It saved us a lot of time here. Otherwise, we would be wasting time trying to calculate where the x-intercepts were going to be, even though there aren't any.
Mr. C, I see what you mean, but what would happen if we didn't notice that it was going to open downward and we tried to figure out the x-intercepts anyway?
Yeah, like, I have the same question as Ruby. If we used the quadratic formula, or the product sum method, like last time, to figure out our x-intercepts, are you saying it wouldn't give us any answers at all? How is that even possible?
Excellent question, you two. That is what I'm saying. Let me quickly show you what I mean. What would happen if we plugged in our a, b, and c values, -1, -4, and -7, into our quadratic formula this time around? Since we know this parabola doesn't have any x-intercepts, how is the quadratic formula going to show us that? Let's try it. We get -4, where the negatives cancel out to give us +4, plus or minus the square root of -4 squared minus 4 times -1 times -7, all divided by 2 times -1. Now, can anyone see what's about to happen under the square root sign? The square root of 16 minus 28 means the square root of -12. That's a problem. We've learned that negative numbers don't have real square roots. No number, anywhere on the number line, can ever be squared to get a negative answer, like -12. So when we plug in a, b, and c from our equation into the quadratic formula, look what it's giving us. No real answers. Just a solution that has the square root of a negative. That's how it tells us that our parabola has no x-intercepts.
Thanks, Mr. C. I understand now.
Like me too. So I guess we would just be wasting our time if we did all of that, because we wouldn't end up with any x-intercept we could graph.
Exactly, Bones. And now that we know there won't be any x-intercepts, we're going to need at least 2 other points, because we need at least 3 points to graph a parabola. So what's the next point we should try to figure out?
Our y-intercept, since that's an easy one. We just plug in 0 for x in our equation. Everything zeroes out except the number at the end, the c value, -7. So our parabola crosses the y-axis at -7.
Excellent, Codette. Let's add that y-intercept to our graph. And now we can connect these dots to draw that arm of the parabola. We just need one more point that we can graph. And this is where our axis of symmetry comes in handy. Remember, the axis of symmetry is the imaginary line running through our vertex. Anything on one side will have a mirror image on the other side, the same distance away. We know that our parabola crosses the y-axis down here at -7, so let's reflect that point across the axis of symmetry. There will be another point at -7 that's as far left of the axis of symmetry as our other point is to the right of the axis of symmetry. It's right here, at -4, -7. We can connect those dots to draw the left arm of the parabola. And that's it. We've drawn our graph. Well done today, class. We've learned how to graph a parabola by hand, using nothing but its quadratic equation. That means we've reached the end of our unit on quadratic equations. I just want to say how much I've enjoyed teaching all of you. You've been a fantastic class. Good luck to you in the future. I'm going to miss you all.